Here we're going to discuss problem 2.12, which is Newman projection, and we're going to write down Newman projection for propane. So keep that in mind. Propane has 3 carbon, and then you fill in with hydrogens. Obviously each carbon must have 4 bonds. So I'm going to write down all the hydrogens before I write down Newman projection. Now we need to write down Newman projection. So let me write down here Newman projection, most stable as well as least stable. So most and least stable conformation. Now let me remind you about conformation. Conformations, you can go from one to the other without breaking any bond by simple rotation. So in Newman projection, you only focus on 2 carbon. You'll be looking at 1 carbon, the other carbon is going to be behind. So in this case, let's now highlight those 2 carbon that I'm going to focus on, and I can now write down Newman projection. C, this is the carbon you're looking at. This is this carbon that you're looking at. If you make a model, then you can better see it. So, and in Newman projection, we don't write down carbon, rather we just write down a dot where you're looking at. So the carbon that you're looking at, which is this carbon, will be shown as a dot, and the carbon behind it, this is the carbon behind it, is shown with a circle. And make sure you align this molecule in such a way that you're looking at this carbon and the other carbon is directly behind, and that's how it's shown. And now I'm going to write down the bonds. Okay, one of these would be occupied by methyl group, so let's write down a methyl group. It doesn't matter where you write down, but just select this one, and the others are hydrogen, and these are the other 2. So I'm going to write down hydrogens. That's attached to the front carbon. We are calling it front carbon, and the carbon at the back, this is the carbon at the back, this is carbon at the back, in this case shown with a circle. Again, I'm going to draw bonds that's attached to the carbon at the back, and in propane those are all hydrogens. Now this is the most stable conformation of propane. Why it's most stable conformation? First thing is staggered, and staggered makes methyl farthest away from hydrogens in this case. Now, so this is most stable, so let's write down most stable. If you rotate this, these groups, hydrogen, hydrogen, and methyl, and so I'm thinking about rotation like this, so that now methyl group could be coming right in front of the hydrogen of the back carbon. So now it'll look like this. Again, this is my front, which is the dot, and now I'm going to show, keeping my hydrogens of back carbon intact because I didn't rotate that. So let's keep it the way it was. That's attached to the carbon at the back. Now carbon in front, remember we moved around this, so around that CC bond. So now in this particular case I'm drawing with a dotted line. Is basically the methyl group is no longer in a staggered position. It's like right in front of this hydrogen, and that makes it unstable, less stable, because they try to stay away from each other. So this is hydrogen, this is hydrogen. Hard to draw, but that's why I'm drawing the dotted line. So this is least stable. I'm going to show you a video clip after 2.13, which is on butane. (2.13) is similar question, but in this case you'd be looking at butane. 1, 2, 3, 4. Butane without the hydrogen. Again, we need to draw Newman projection. So I'm going to consider these, and you need to draw, again, just like before, most stable as well as least stable conformations. So I can write down a number of conformations here. So let's focus on this carbon. So that carbon will be shown as a dot. This is the carbon at the back. So that will be shown as a circle. Now let's draw atoms bonded to the front carbon. And obviously you have a methyl group. Let's write down the methyl group attached to the front carbon. So this is the methyl group. And obviously there are two other hydrogens, because that carbon must have 4 bonds. So let's now stick in those hydrogens. Now the back carbon, this is the back carbon. Now we are focusing on the back carbon. Also have the methyl group attached. So that's the methyl group attached to the back carbon. So let's first draw those lines. Sorry, that line was not straight, but I meant to draw a straight line. Okay, now stick in methyl group and 2 hydrogens. So there's 1 hydrogen here, the other hydrogen here. So I'm going to write down that. Now question is, where are you going to write down the methyl group? Well, there'll be more than one possibility. If I write down methyl group of back carbon here, I can now write down hydrogen here and hydrogen here. That's one possibility. The other possibility is, again, I can write down the front carbon as a dot, the back carbon as a circle. Now I'm going to write down, again, these are staggered because I'm looking for the most stable conformations. Remember, you go one conformation to another by simply rotation around the carbon-carbon single bond. We're talking about this carbon-carbon single bond. Okay, now let's keep the first methyl group intact, and obviously we had other hydrogens. Now instead of putting methyl group here, I'm going to put methyl group completely opposite side of the first methyl group. And then now stick in hydrogens. Between these two staggered conformations, keep in mind staggered conformation is more stable than eclipsed conformation. But now we have 2 staggered conformation. This is one, this is the second. If you examine rather carefully, you know that this is the most stable conformation. So let's call it most stable. Now why this is most stable? Because the two big groups, methyl is a fairly big group, they're farthest away from each other. Whereas in structure 1, even though it's also staggered, two methyl groups are much closer to each other. So this is the most stable and this is less stable. I would not call it least stable. To be least stable, it has to be one of the eclipsed conformation. You remember the eclipsed? Let me redraw one of those. Front carbon, back carbon. Now, eclipse is they're right. So among eclipsed, I can have two methyl, one in front, one at the back. Hydrogens, hydrogens, hydrogen, hydrogen. This is going to be the least stable because these two large methyl groups are facing each other. So this is going to be least stable. However, I can have another conformation of eclipsed. This is also eclipsed. And another eclipsed conformation. Eclipsed means when these groups are facing each other. Okay. Again, this is another eclipse I'm going to draw. It's hard to draw because I just want to show you that one is in front and the other is behind. Okay. So I may have one methyl group here, and this time it's not right in front of methyl group, rather in front of a hydrogen. So I can put another methyl group here in any one of these other ends, methyl group and hydrogen. Keep in mind they're front and back, and hydrogen and hydrogen. So these two are eclipsed. This one is least stable. This is stability wise more stable because now methyl is not facing a methyl, rather it's facing a hydrogen. Okay, so these two are eclipsed. And first two are staggered. Conformation. Now try to build a model, and I'm going to show you next in a video clip that I made a molecular model for butane, and I'm going to show you the most stable and least stable conformation, so you can watch it carefully. Now I'm showing you the model of butane. This has 4 carbon. You can see this, all the 4 carbons. These are the black ones are the carbon. And I made methyl groups more colorful so that you understand that, even though these are hydrogens at the end, but those are really part of the methyl group. So I have one methyl group here and the other methyl group here. Now I'm going to show you the Newman projection. In order to look at this molecule according to Newman, you'll have to turn this molecule in such a way you're looking at this carbon, which is shown as a dot. I don't know whether you're seeing it in the right orientation or not, but I'm focusing on the second carbon, and the third carbon is right behind me. And this methyl group you can see here, now that's in staggered position compared to these hydrogens. Now I can rotate this. If you can see it, I can rotate this. So this is the most stable conformation because I have methyl group farthest away from each other. So these are the two methyl groups farthest away from each other. Now let's get least stable conformation. Now look at the least stable conformation. Here these two methyl groups are pretty close to each other. So we call it steric hindrance. These groups don't like to be that close to each other. And that's exactly what we wanted to explain here. Here we're going to discuss problem number 2.15C. Basically, you need to convert a skeletal structure to molecular formula. So let's do this problem, and let me first draw this. You have a 6-membered ring and then a 5-membered ring. You have a nitrogen. So let's draw it. Okay. Each corner must have carbon if nothing else is shown. If you have any element other than carbon, then it will be shown. Just like in this case, they are showing you nitrogen. And then you have a double bond, single bond, double bond, single bond. This is aromatic. That's double bond. Okay, so this is how it is given in the book. Now you need to figure out molecular formula. In order to write down molecular formula, you first need to write down these elements explicitly. Like, for example, each corner has carbon unless some other element is shown. So that's the carbon, that's the carbon, this is a carbon, this is carbon, 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 carbon. Next, we need to fill in with hydrogen. Keep in mind that nitrogen must have 3 bonds. So you must have 1 hydrogen. I think this hydrogen was given in original question, attached to nitrogen. So that makes 3 bonds around nitrogen. But hydrogens are not shown. So we need to stick in those hydrogens. This carbon already has 3 bonds, double bond on one side and single bond on the other side, so it can only hold on to another hydrogen. So it can have 1 hydrogen here. Similarly, next carbon can attach to 1 hydrogen. Now, if you look at carbon, which is part of the fused ring, 2-ring structure, this carbon has 4 bonds already there. Okay, keep that in mind. This is 1 bond, this is a 2 bond, and the other 2 bonds are here between these 2 carbon. I think I made it a little messy, but there'll be no hydrogen there. Same is the case with this carbon, already has 4 bonds because of a double bond and then 2 single bonds. Now what about the other carbon? This carbon has 3 bonds, so I must have 1 hydrogen. Similarly, this carbon should have 1 hydrogen, and this carbon has 1 hydrogen. This carbon has 1 hydrogen. So now I'm pretty much assigned all the hydrogens, keeping in mind that carbon must have 4 bonds, nitrogen must have 3 bonds in a neutral compound. Now let's count. So since it's a hexagonal ring, so this is the hexagonal ring, so I can quickly say that this has 6 carbon, then 7, this is 7th one, this is the 8th carbon. So carbon 8, and then let's count hydrogen. 1, 2, 3, 4, 5, 6, 7. H7, and I have 1 nitrogen. So that's the formula of this skeletal structure. So whenever you have a question like this, always keep in mind that carbon must have 4 bonds, and you need to fill in with hydrogen if hydrogen is not already shown. So that's how you need to do it. Next, we are going to do 2.47. In this question, you are supposed to name a compound, and of course, if there are cis-trans isomers, you must identify that. So first you need to look at the structure. Let me draw the structure. Okay, so it's a 6-membered ring. And then you have bonds shown with thick lines or wedged lines, and that this kind of lines mean that those bonds are projected towards you, because these are three-dimensional. When you do not have a model in front of you, these are helpful by looking at thick bonds and dotted bonds. And this one is hydrogen. And then you have a dotted line or dotted bond. So dotted bond for a group going to the back of you. So that's methyl group. And I have also dotted line or dashed lines for hydrogen. Now how do I read this? This thick line represents methyl group is projected toward you. The other methyl group with dashed lines are behind you. Now for cis-trans isomers, you only need to focus on the groups other than hydrogen. So substitution groups are anything other than hydrogen. In other words, I could have had Br, Cl, NO2 group. So those would be substitution group. So in this case, I have these two substitution groups. Now, next question is, are they both on the same direction or in opposite direction? They're in opposite direction because one has a thick line, which is toward you. The dashed line is away from you. So that means it cannot be cis, rather it has to be trans. So in naming this compound, I'd first write down trans. In order to be cis, both will have to be along the same direction, on the same side of the plane of hexagonal ring. So this is going to be trans, and after trans you should write down a dash. That's a conventional one. Then this is a cyclic compound, so I must start numbering where these substitution groups are attached, 1 and 2 obviously. That gives you the smallest sum. So it's going to be 1, comma 2. Between two numbers there'll be always comma, and then between number and letter there should be dash. We have two methyl groups, so I must call it dimethyl. So dimethyl cyclohexane. Okay, so that's the name of this compound. Now we're going to discuss 2.47D. Again, this is IUPAC names. So I'm going to first draw the structure, and then I would try to name the compound. Obviously, this is cyclobutane because there are 4 carbons at one carbon at each corner. Then you have 2 groups, one shown with thick line. So it's exactly shown like this, CH3, CH3. And the other group is shown with the dashed line. Now, before I name this compound, first I need to know whether these two groups are on the same side of cyclobutane or they're on opposite sides. Since one has the thick line, the other one has dashed line, obviously they are opposite. The thick line substitution group is toward you and methyl group is away from you. Now what group is this? Keep in mind this corner also has a carbon. So that means this is a carbon and that has branching next to the last. And this is isopropyl because you can think it this way. This is the carbon and this is the branching. This is the branch. So that is isopropyl. So that's isopropyl group. So we have isopropyl group. It's a good idea to write down first the substitution groups. Isopropyl. And the other one is the methyl group. Now the question is, which one are you going to assign 1 and which of these carbon would be assigned 2? Now I mentioned about alphabetic priority. Iso, I comes before M. So that has to get 1. And obviously the other one gets 2. Now here I want to mention to you that iso is considered to be part of the name. On the other hand, sec, tertiary, tart are not considered to be part of the name. Those are considered to be prefixes. So in other words, in alphabetic ordering, you don't count sec or tertiary because they are counted as prefixes and you can ignore them when you are thinking about alphabetic order. Okay, anyway, so this iso group gets 1 and methyl group gets 2 because of alphabetic priority of I over M. Now, we also know this is trans because one group is toward you, the other one is away from you. So I'm going to write down now trans, and then there is a dash, and then 1 isopropyl with capital I, because we are beginning that name. So 1 isopropyl, in the second position is methyl. Again there'll be dash, number and letter there'll be dash, methyl, smaller letter. So 1 isopropyl, 2 methyl, then I need to name this ring structure, which is 4-membered. 4-membered is butane, and it's a cyclic structure, so it's cyclobutane. So you need to write down as cyclobutane.